I'd like to practice another problem of this type. Yeah, so let's say that we were already handed an integral. So convert the integral 0 to 1, integral 0 to root 1 minus x squared of the function x squared plus y squared dy dx. So we could do this integral directly, but it's probably going to be a lot of work. So instead, let's take this integral and convert this into a polar integral. So integral using polar coordinates, and then evaluate. So the original integral here, oh, it's going to be a lot of work. Okay, so instead, let's draw a picture. So first of all, we'll notice that x. So in the region we're talking about, x goes from 0 to 1. Okay, and then y goes between 0 and root 1 minus x squared. So look, the um, inequalities for y tell us we're talking about filling in the top half of a circle of radius 1, but then x only going between 0 and 1 tells us we're only getting, so instead of, so instead of getting, so for the circle, instead of getting all of this, which is what this part would suggest, we also have this restriction that x should be not negative, so we actually only get this part right here. Yeah? So it's just, there'd be certainly other ways to write in inequalities that describe this same region here, but this is the one that we were given. And so if we were to describe the same region in polar coordinates, so here's the rectangular description, but in polar coordinates, so we'll see that theta goes between 0 and pi over 2. We'll see that r goes between 0 and 1. Yeah, so this integral right here, we're not going to compute it directly. We're instead going to say it is equal to the following double integral that's written in polar coordinates, which the dy dx, which is dA, is going to now become replaced with an r dr d theta. Okay, and then since theta is on the outside, goes from 0 to pi over 2. Since r here is on the inside, goes from 0 to 1. And yeah, that's copied from over here. And then x squared plus y squared. Now we can go through all of the mess of turning x into r cosine theta and y equal to r sine theta, but we can also just use another equation that we got from polar coordinates, namely that x squared plus y squared is equal to r squared. So take a look at how nice this integral is. I mean, integral 0 to pi over 2, integral 0 to 1, r squared times r cubed, dr d theta. This is so awesome. So we got the integral 0 to pi over 2. Integrate r cubed with respect to the variable r. Theta is treated as constant. So we'll have r to the fourth over 4 evaluated at 1 and at 0, d theta. And we have integral 0 to pi over 2 of plug in 1, so 1 to the fourth over 4. So you get 1 fourth minus 0 fourths. We won't write minus 0 fourths. Okay, d theta. Now we're again integrating a constant. So we'll plug in theta, integrate, and so that 1 fourth times theta, and then we need to plug in, so we need to plug in pi over 2 for theta, we need to plug in 0 for theta, so we have 1 fourth times pi over 2 minus 1 fourth times 0, so we won't write that. In the end, this will be pi over 8. Pi over 8. Whoever over 8 pi. Ah. Okay, so cool. We did this integral not by computing it directly, yeah, but instead we didn't do this direct integral. It just happens to be equal to this integral in polar coordinates. So sometimes things are more convenient. I know that this r extra in in the dA is kind of strange, but we kind of went through where it sort of came from. And it seems strange, but the whole point is, even if polar coordinates might be a little iffy, there are times that at least converting into polar coordinates means that the integral is much, much nicer to do. Next time, we're going to do this. So we had seen, let's say this time, we had seen uh, the value of r being stuck between two constants a and b. Next time, what happens when r is stuck between two functions of theta? So h sub 1 of theta, h sub 2 of theta. This process looks a little strange, but it won't be too bad.